Good afternoon once again. My name is Mohammed Sarmad and I'm presenting our research article on behalf of my research team from the University of Salento in Italy. So our topic was to introduce hyperparameter effect in conditional diffusion model for accurate sea surface temperature and its reconstruction. So the question is why we need accurate sea surface temperature representation. So first, I want to talk about my background that we are working on data assimilation for oceanographic data. And during that application, we are working on diffusion models to be implemented in sea surface temperature as a variable, as a single variable. So this accurate sea surface temperature representation is essential for climate modeling and weather forecasting. Why? Because in traditional ocean models, they often exhibit biases due to resolution and observational coverage limitations. For this study was to explore the effect of hyperparameters in diffusion model for improving sea surface reconstruction. So, the oceanographic is basically the ocean systems, which includes physical, chemical, biological, geological aspects of essential for understanding climate, weather, and marine ecosystems. Its importance is that it plays a crucial role in weather patterns, ocean currents, and climate modeling. It also impacts the ocean forecasting and marine resources management. So the study is basically to enhance the sea surface prediction using conditional diffusion model and improve oceanographic data assimilation for better climate forecasting and marine applications. So talking about diffusion models, how it works. Diffusion model basically work with two process. First one is called forward process and the second one is reverse process. In the forward process, we add Gaussian noise over multiple steps until we get a whole noisy image. After that, we learn with the convolution network to denoise it, which is called reverse process. So these two processes are combined in a diffusion model. Why we chose diffusion model instead of other GANs? They are more stable. Their likelihood-based training is a good plus. Also, it doesn't include any adversarial setups. So we have two kind of diffusion models in literature and to implement, but what is the difference between both of them? In our study, we are using conditional diffusion model, which is a model as a type of a generative model that produce output based on specific input conditions. While the unconditional diffusion model generates samples without external guidance. Conditional model modify the denoising process by incorporating external inputs such as simulated SST in our case into the reverse process. In the case of DDPMs, the model learns to predict the noise at each time step conditioned on the input. This allows the network to generate samples that are both realistic and consistent with the conditioning data. It also effectively learns a guided reverse diffusion path. Conditional diffusion model offer more control over the generation process and can produce more targeted and realistic outputs compared to the unconditional models. So, what are hyperparameters in diffusion model? Hyperparameters control the learning process and structure of the model. In diffusion model, the hyperparameters directly influence the ability to denoise and reconstruct the data. Optimizing hyperparameters can lead to significant improvement in model performance, such as more accurate reconstruction, but also with the help of this variation, you can control the memory usage and the model performance. So in our study, we explored some hyperparameters, which includes the number of base channels. Basically, the base channels are the first outcome of the first convolution layer, which tell us how many features are explored. So it controls the model capacity to learn from the data. And then increasing the training epochs, it affects the denoising process and quality of reconstructed sea surface temperature data using lower channel depth. Then we also explore learning rate, which adjust the speed of the model's learning and convergence. Also, we try to assess the model's temporal generalization capability by assessing the robustness of our diffusion model. So the parameters that we have explored, and some are constant. We change our base channels from 8, 16, 32 until 256. Then for the time embedding in the diffusion model, we use sinusoidal embedding. For conditioning strategy, we use simple concatenation of our simulated SST with a noisy input image. Noise scheduler, we use the same in every case. Diffusion steps, we took 1000 steps as it was already in the literature, so we just keep it constant for every experiment. The loss function was mean squared error between predicted and the actual noise image. Then we vary learning rates from very low and high, and see their performance, that which one performs better. For the optimizer in the diffusion model, we use Adam optimizer, and we use two data sets, one as an input and the other one as conditional input. So we use sea surface temperature simulation data, and which is a numerical model data obviously, and reanalysis data, which is the realistic data, which offers often sometime have errors. So we try to predict the data which is very close to the sea surface simulation. For the area of concern, we took the southern of Italy, especially the Puglia region in which we are already located. So we use the southern of Italy domain of Mediterranean Sea. So as a base, we use a conditional diffusion model with the unit architecture. We tune different hyperparameters and tested across different configurations to assess their impact on sea surface temperature reconstruction. A systematic approach was taken to explore the relationship between hyperparameters and the model performance. So our model architecture consists of few blocks, starting from the input processing. Input processing consists of noisy image as an input and a conditional input, as we call it simulated SSD. Both are passed together, a 3x3 convolution process, and then time embedding encodes the current time step of the diffusion model. Then we have the down block, which we usually say as encoder. It applies resonant time embedding and conditional concatenation. And then we move on to the bottleneck mid block, which also implement all three steps: so resonant block, time embedding, and conditional concatenation. Moving forward, we use up block. In the up block, we use all three of the above, using resonate, time embedding, conditional again, but also we use skip connections this time. And then our output layer gives us the output, and in the conditioning, we injected at all levels, ensuring output fidelity to be external outputs. So experimental setups, we use two data sets, simulated sea surface temperature data and reanalysis data. The hyperparameters that are being varied and explored are the number of channels, number of training epochs, and the learning rate. To assess the model's temporal generalization capability, we also analyzed its performance in predicting sea surface temperature across different seasonal batches. The model was trained with the different configurations, and performance was measured by bias reduction and sea surface temperature reconstruction accuracy. So before going to our findings, let me recall everything that we use two data sets, one as an input, the other one as a conditional input. So one is reanalysis data, the other one is simulated data. The domain we used is the south of Italy, especially the Puglia region. The parameters we explored was base channel, learning rate, number of epochs, and at the end we tried to make seasonal batches and explore its generalization. We use a Markovian noise-based generative process known as DTPM, very famous, learns a conditional reverse process guided by simulation. It reconstructs physical aligned high resolution sea surface temperature, which bridges modern machine learning with classical oceanographic forecasting. So our first parameter that we tried to explore was the changing the number of channels. So the channel depth obviously affect the model performance. So this graph, as you can see, shows for the different base channels from 8, 16, 32 until 256 on the model loss during the training. So this represents the average loss that is being achieved after every epoch for the all base channels from 8 to 256. So you can realize and analyze from the graph that as the number of channel increases, the model converges faster and achieves lower loss. As a high base channel count provides the model with more capacity to learn complex patterns from the data. But as we know that increasing the base channel, we are also playing with high memory usage. So we need to take in account the usage of memory as well. So here is the inference image, which we implemented our number of channels for a different number of channels for our diffusion model. As I told you before, we use two inputs. One is the simple noisy image, which is reanalysis, and then we have a conditional input, which is simulated data. So simulation and reanalysis both were given as input, and we got an output which is biased corrected in output. And the last column, the difference is basically the difference of biased correction and the first image, which is reanalysis. So the difference between them is given as output. So because we are trying to predict our simulated data, which often have some errors or some inconsistency, and to compare our output as the numerical input. So the difference between them is given in the last column. The figure shows the effect of varying the number of channels of the model on sea surface reconstruction. The images on the left show biased corrected sea surface temperature using reanalysis and simulated data. The color bar on the right side indicate the corresponding reconstruction error. The hyperparameters are optimized. The error, the bar in the red, decreases, leading to more accurate sea surface temperature reconstructions. So to to see our results in metrics, we compute different metrics to calculate and to see mathematically that how these are. Because if we go in the previous one, if we see it in a real time, and if someone is not that much intelligent or not that much aware of the problem, then he may not verify the exact difference when we go from 64, 128 and 256, because the difference is very minor. But then with the calculation, we find out that the base channel of 250 shows the best performance across all metrics. Lower base channel 8 and 16 exhibit high error and low correlation. Increasing the base channel improves the accuracy and reducing the error and improving correlations. The base channel of 128 and 256 achieve nearly perfected reconstruction with very low mean square error, root mean square error, and very high precision correlation and R square values. Then to the next step, we explored that yes, increasing the number of channels affect the performance, but if we have some constraint of the memory and we are not able to use a lot of memory because of the model parameters, what we can do is we can improve the number of epochs and see if the performance of the lower base channel can be compared with the higher one. So we try to increase our training steps. We move from 2000 until 10,000 epochs. As I told you before, the first experiment that I have mentioned was just for 1000 epochs. So as a result, the difference became very narrow when we increased the number of epochs of a lower base channel, like 64 in this case. As the training progresses, the quality of generated sea surface temperature field improved markedly. Absolute error maps in the bottom row of the figure, it significantly pixel-wise deviation between the generated and ground truth sea surface temperature. The earlier epochs like 2000 or 4000, the large area of elevated errors are evident. Uh, Also, it's difficult to analyze like with the naked eye on this slide because this need to be more, but the error is very less, so that is why it is more not more that significant. But with the matrix calculation, we can prove this thing. But again, with the continued training, the error diminishes progressively, and by the time of model reaches 8,000 to 10,000 epoch, the error magnitude and spatial are significantly reduced. So the point is that if we have a constraint of a memory, we can increase the number of training steps, and we can still achieve a good output accuracy. So to analyze it with the matrix, we again calculate all those matrices for the all the steps from 2000, 4000 until 10,000 epochs. And as you can see in the 10,000 epoch, when we achieve this step, it caused a little bit of an overfitting problem. So the best performance was done by 8,000 epoch, and in the 8,000 epochs, all the matrices proves that this one is performing around 256 base channel at 1,000 epochs. So it's a need-based stuff that if you have more memory and you want to process your model very quickly, you can increase the base channel. But at the same time, if you have some constraint of the memory, you can increase the number of epochs with a lower base channel and still you can achieve the accuracy. So the next explored parameter was learning rate that we use in different literature for the diffusion models. We have seen the learning rate between 10 raised to power minus 5 and minus 4 mostly. But just to explore, we try to explore different values from higher to lower values and to see their performance, that how they behave during the model. So we again fix our epochs to 1000, and then we do the same experiments. And the key observation was the larger learning rates result in poor convergence with the loss stuck at high values, which suggests that the optimizer overshoot the minima or get trapped in suboptimal region. But then again, learning rate of 10 raised to power minus 4 produce fast and stable convergence with the final loss of approximately 0.0025. And then going more or less, learning rate showed slower convergence with 10 raised to power minus 5, resulting in marginally higher loss than the 10 raised to power minus 4. So from this analysis, we took 10 raised to power minus 4 as our learning rate, and we perform the model. We perform our reconstruction using this learning rate. So when we explored all those hyperparameters, we want to see the generalization capability of our model. That yes, we are doing it for 1 year. It is producing good inference image, but is it possible that we can implement in different seasonal batches? So instead of going for spring, autumn, summer, and winter, we make it a bi-monthly and try to explore the model performance based on bi-monthly batches. So we actually wanted to assess the model's performance across seasonal batches. So the key result was the key outcomes were the slightly higher errors recorded for November, December, and March, April batches, which may be likely due to the due to greater sea surface temperature variability, because when we are having transition from one season to another season, maybe that is the main issue that cause a little bit of higher error, but still it's very less. So again, we calculate all the matrices as above, and all these also shows that yes, when we are moving from November, December, and again from March, April, which is the transition period of two different seasons, yes, our model do a little bit of variation in the performance. But as you can see in the inference image, we made for January, February, March, April, May, June, July, August, September, October, November, December, all 12 months into 6 bi-monthly batches. And the difference between the reanalysis, which is input image, and the output biased corrected image is very less as before. So just to conclude my study, that this study shows the increasing base channel depth improves the accuracy of conditional diffusion model for a sea surface prediction. But gains become more marginal beyond 64 channels due to higher computational cost. These insights guide the use of diffusion model in ocean modeling, weather forecasting, and climate simulation, especially when the computational efficiency is important. Further work could explore multivariable conditioning, like we instead of just temperature, we can use salinity, we can use eddy currents and stuff like this, more variables. Also, we can go to 3D reconstruction and real-time integration. The accurate representation of coastal feature is vital for reliable ocean forecasting. Marine sources management also. The misrepresenting of coastal dynamics can lead to a significant error in the application like habitat modeling and marine heat wave detection. While the model performs well in the Mediterranean, as I told you before, we are working on data assimilation at the Mediterranean Sea. So we take a very small part of Italy, which is the southern part, Puglia, and it is also scalable for broader regions and additional variable like salinity, velocity, and there may be currents as well. So that's all from my side. If you have any question or you want to discuss something.